All right, 2-4 notes here. Introduction to transformations. If you're in my classroom, then I will say notes are going to be ultra important in this unit. And so as we're working here, let's talk about transformations. Transformations, just like transformers, they're going to make changes. You're going to have something that's making a change to itself. And so the first key word here is the word isometry. Isometry is a transformation or change which stays the same size and shape. So again, it's a transformation or change which stays the same size and shape. And that's going to be what we need to talk about or need to know as far as what an isometry is. And then the ones we're going to start out with here are all types of isometries. So reflections, translations, and rotations are all examples of isometries. They all stay the same size and shape. They're all changes in position. What is something that would be a non-example? A dilation. Or if I think of a triangle that is all 60-degree angles, and then a bigger triangle that is also all 60-degree angles, the only difference is one is larger, but the angles themselves are the same. So they're very similar. It's a transformation where we just made it larger. We changed its size. Right? And so reflection, if you don't know, reflection means to flip, then put that in your notes. All right, but I'm either going from up high to down low or from side to side, but I'm reflecting across. For us, we're going to talk today only about reflections across the axes. And so these notes are going to be the ones to get in. So reflection across the x-axis uses this rule. This is our rule we're going to use when we're doing that. And so xy becomes x opposite y. And so if my point P is -1, -2, and I want to reflect it over the x-axis, then my P image, that little mark right there, this little mark means image. If I'm looking at a thing over here, a drawing, and I have A and A image, I know A is the original one and A image is the new one. So this little mark right there means image, and that means it's the new one. Now it says the rule is x stays x, but y becomes opposite. And so -1 stays -1, but -2 becomes +2. And so that is how I read and use these rules. And once you get used to it, these rules are going to be super helpful. And so that's why you should have them in your notes. And then we have reflection in the y-axis. Reflection in the y-axis uses this rule right here. xy becomes opposite xy. Again, this becomes a lot easier if I have these rules down in my notes. And so make sure you do. I'm actually going to skip part A of this example. Now, I am going to use these points, 3, 2, 2, -2, and 4, -5, but we're going to look at part B. Right? And so notice here they took all 3 of those points. A is at 3, 2, B is at 2, -2, and C is at 4, -5. And now we said we want to do a reflection in the y-axis. So I had to go, okay, what's my rule for that? Well, this is my rule. xy becomes opposite xy. So A image became -3, 2. Opposite x, 3 became -3. 2 stayed 2. Y stayed y. So -3, 2. -1, 2, 3, up 2. So like right there. And then B was -2, -2. So like right there. C was -4, -5. So like right there. And again, those would be A image, B image, C image. And I would graph that if I wanted to look like it got reflected over the y-axis. But mostly in your homework, you're just going to be making this list of points. And so in your homework, you're going to say, A is 3, 2. And then use your rule. You're going to say A image is -3, 2. Translations. First thing I need to know about translations, if I don't know it already, that means to slide it. Slide it up, down, left, or right. All right, up, down, left, or right, or on a diagonal going like up and right, or down and left, or down and right, or up and left. All right, and so we're going to just slide it in a direction. Now, probably one of the important things, okay, so this is the note for translations. Translations will always have a vector. All right, notice it's inside, like, translations will always have a vector. And notice here, it's like inside parentheses, but they're like pointed parentheses. Kind of to me look like sideways V's for vector. Right? And that's A comma B there. And so once I know the vector, I use this rule. XY becomes X plus A, which is the first thing in the vector, Y plus B, which is the second thing in the vector. And so if my point is -2, 3, and my vector is 7, 4, then my P image is, I would take this -2 and add 7 to it. And so I get 5. And then for the Y, I take this 3 and add 4 to it. And so 7. And so P image is at 5, 7. And so your homework problems look like this. And so first I'm going to make a list. Q is -8, -2. R is -9, -5. S is -4, -7. And T is -4, -2. And so those are all going to become new points. Q image, R image, S image, and T image. After I use the vector, which is it gives me right here. So I'm going to add 7 to the X, add 7 to these X values, add 1 to the Y values. And so -8 plus 7 is -1. -2 plus 1 is -1. Then I got to go down here to -9 plus 7 is -2. -5 plus 1 is -4. For S, -4 plus 7 is +3. -7 plus 1 is -6. -4 plus 7 is still 3 for T image. And -2 plus 1 is -1. And so I made a new list of coordinates along this vector by adding 7 to the X values and 1 to the Y values. Take a minute and track this one. What do you think it is? A, B, C, or D using the vector 4, -9? All right, you can continue to pause the video if you haven't come up with it. I thought of it just as the point M, -2 plus 4 is +2, 1 minus 9 or 1 plus -9 is -8. And that meant that C is the only one that worked. Next we have rotation, and if you don't know that rotation is to turn it, then please make a note of that. And then we have lots of rules to go on here. The first rule has to do with a 90-degree rotation. Right? And so this is my rule with a 90-degree rotation. Now it's going to say 90 degrees counterclockwise, which means we always are turning from quadrant 1 to quadrant 2 to 3 to 4 counterclockwise. I'm never going to try to trick you with this in our geometry class. So it's never going to be like clockwise. You have to realize that that's the same as 270 counterclockwise. So if it ever says 90 degrees, don't worry about the counterclockwise word. That means 90 degrees, and this is our rule. 180 degrees rotation is right there, and that is the rule I want to use with it. And so first, let's go over both these two rules. I kind of just talked through it here. So the first rule, xy becomes opposite yx. We'll show an example here real quick. Xy becomes opposite x, opposite y. And then last one is this 270-degree turn. 270-degree turn, xy becomes y opposite x. And so if I have just the basic point at, like, let's say 5, 2, and I want to talk about a 90-degree turn, a 180-degree turn, and a 270-degree turn. A 90-degree turn uses this rule here. So xy becomes opposite yx. And so xy becomes opposite yx. And so y was 2. The opposite of 2 is negative 2. X was 5. And so now the last part is 5. So that's the new point, negative 2, 5. For 180 degrees, it's pretty easy. I'm just using this rule. Xy becomes opposite x, opposite y. And so the opposite of 5 is negative 5. The opposite of 2 is negative 2. And for 270, I'm using this rule down here. Xy becomes y opposite x. And so the y was 2, and that just goes first now. The 5 becomes opposite, so it's negative 5. And again, these would all be P image based on the change or the rotation that we did. And so again, for this one, I'm going to make a list of points. F is 2, 1. G is 7, 1. H is 6, negative 3. And J is 1, negative 3. And again, and now it's telling me that I'm making a 180-degree rotation, a rotation of 180 degrees. And so I go back and look at my notes. 180-degree rotation was x, y becomes opposite x, opposite y. And so for F image becomes negative 2, negative 1. For G image becomes negative 7, negative 1. For H image becomes negative 6, positive 3. And J image becomes negative 1, positive 3. They are all opposite of what they were originally. Last thing we're going to do is just to identify what kind of transformation or what kind of isometry is occurring. And so our answers are all going to be rotation, reflection, or translation. And so for this one, it's the teacup ride at the amusement park. Riders sit in each cup, which turns as the ride turns itself. So the cup's turning and the ride's turning. What type of rigid motion is shown? I think we know this key word is turning, and turning is rotation. For these examples, it always is going from the blue to the green. from the blue to the green. A can be tricky. So can B, actually, but A can be very tricky. A lot of people look at that and immediately think reflection, but it kind of also slid up. And so I think it's best described as just a translation. Now for B here, B I think is best described as a reflection from the blue to the green. But in our class, it doesn't really fit our definition that we're using for 100-degree rotation because we're talking about the origin. But if you told me it was a 180-degree rotation, I don't know that I could argue with you. There is a point in space upon which it is rotating 100 degrees. But the best answer there is reflection. And then this one is a rotation, or if I wanted to be specific, a 90-degree rotation. Sometimes I get the question, how did I know it was 90 degrees? Well, let's say I call this one A and this one up here A image. From the origin, which we're rotating around, the distance here to A is the same as the distance here to A image. And then if I was to measure that, that would be a 90-degree angle. So it was a 90-degree rotation. Here is the problems for you to try. I wish you the best of luck.